Okay, we're going to continue looking at applications of Newton's second law. Here we have an example. Two forces, 90 newtons and 100 newtons, act on a 1 kilogram object as shown. So we have the 90 Newton force going along the y direction and the 100 Newton force going along the x direction. And the problem is to determine the acceleration of the block. Okay, so we've drawn our coordinate system. We have our x and our y lined up with the two forces. We have the 100 Newton force, which is along the x-axis, the 90 Newton force, which is along the y-axis. And since we know that force is a vector, we can add these two forces up, and we'll get some net force, which will be moving off at some angle theta. Now, to find the acceleration, we can use Newton's second law. And we know that Newton's second law tells us that the acceleration is the sum of the forces divided by the mass, and we can see that the sum of the forces is simply going to be that 100 newtons in the x-hat direction plus the 90 newtons in the y-hat direction. We can divide that sum of the forces by the mass, which is 1 kilogram, and that'll give us the acceleration, which is 100 in the x-hat plus 90 in the y-hat, meters per second squared. Remember, a newton is a kilogram meter per second squared, so if we divide that by kilograms, we're left with meters per second squared. And so if we want to know what the magnitude of this acceleration is, we can simply take the square of that and the square of that, and then take the sum and the square root just by the Pythagorean theorem. And that gives us that the acceleration is 130 meters per second squared, or in scientific notation, that would be 1.3 times 10 to the squared meters per second squared. And of course, the angle is going to be given by the arctangent of the y component, which is 90, divided by the x component, which is 100. That's because that's the opposite side, that's the adjacent side. The arctangent of the opposite over the adjacent gives you the angle theta, and that works out to be 42 degrees. And from my picture, that looks roughly like what it should be, and so that makes me happy that my picture and my math correspond. Now, I went through that pretty quickly, but what's the key thing? It's just this formula here. The sum of the forces divided by the mass is the acceleration. And we have the x component and the y component of the net force already given to you in the problem. So a lot of these Newton's second law problems are just doing the vector stuff that you already know how to do now. Let's look at the force of gravity acting on some object m. So this could be an object that's sitting on a table. It could be an object that's dropped out of an airplane and that's falling. But regardless, the acceleration due to gravity is always g. So if this guy is released and able to move freely, it's going to accelerate with an acceleration of g. And so the sum of the forces is equal to ma. But what is a in this case? A is little g. Now, from our coordinate system here, and the coordinate system, remember, our coordinate system is arbitrary, but the way that I've drawn my little blue coordinate system here, I've defined y as being positive pointing up, and so that means that g is going to be pointing in the negative y-hat direction. And so the sum of the forces here, there's only the force of gravity, and we call that the weight. And so we can say that the weight is equal to minus mg y hat. And typically we could say, or we could simply say that W is equal to mg downwards. Both of those cases, I've got both the magnitude, the mg, and the direction, either downwards or minus y hat. So I'm clear about what the components of the force are. And remember, weight is just the force of gravity, and that's going to be the mass of the object times the acceleration due to gravity, little g. Again, it's a mass times an acceleration, but this is a special acceleration, little g. A couple of thoughts here to think about weight. So the first thing that we want to note, weight is simply determined by multiplying the mass times the acceleration due to gravity. Weight is a force, and so typically it'll have a units of a newton or a pound. There are other units of force, but these are by far the two most common. And weight and mass are related because we know that W is equal to mg. And so obviously if the mass goes up, the weight's going to go up and vice versa, but they're not the same thing. And we can see remember, mass is the measure of a body's inertia, and that's not going to change regardless of where you are. If you're on the moon, if you're on the earth, or if you're in outer space, you have the same mass. It's, you could count up all the neutrons and protons that make up the atoms of your body, all the electrons, and all of those things would have a certain amount of mass. And if you go to the moon, unless you like have your arm chopped off, your mass is not going to change. The amount of stuff that makes up your body is not going to change. But what would change would be your weight, because the moon has a much less gravity than the earth, so the little g on the moon is much smaller than the little g on the earth. And of course we know on the earth it's 9.81. If you needed to know what it is on the moon, guess what? You could look that up. It's a well-known quantity. Let's look at another example. In this case, we're going to calculate what's known as the normal force. And so anytime you have an object that is pressed into a surface, we know from Newton's third law that surface is going to press back with an equal but opposite force. And so that force is called the normal force. Now, we can see in this picture, I have a block which is resting on a table, and I have the weight of the block pulling it down. And by the way, the weight always points towards the center of the earth, and effectively that means it's going to be pointing down to the ground. And we know that there will be an equal and opposite force exerted on the block by the table. The block is being pressed into the table by the weight. The table is going to press back with an equal and opposite force, and that force is called the normal force. Now, here's why it's called the normal force. Whenever an object has a force exerted on it by a surface that it's pressed into, that force is always going to be perpendicular to the surface that is pressing into the object. And so, in other words, the normal force, that force is always going to be perpendicular to the surface, which in this case is the table. So this normal force is going to make a right angle with the table because it's going to be perpendicular to that surface. In mathematics, the word normal very often means perpendicular. And so since this force has to be perpendicular to the surface, it's called the normal force. So just remember that in this context, normal means perpendicular. All right, so if we want to actually calculate this normal force, how would we go about doing that? Well, we can do it by applying Newton's second law. Now notice what I have here. I've got a picture, and I've drawn all my force vectors on my picture. There are only two here. There's the weight pulling it down and the normal force pushing it back up. And I've also drawn a coordinate system. Now, where I put the origin of the coordinate system in these kinds of problems doesn't matter so much, because what I'm using it for in these Newton's second law problems is to show me the direction. In other words, to show me which things are in the positive direction and which things are in the negative direction. So here I've defined things pointing to the right as being along the positive x-axis, and things pointing up as being along the positive y-axis. Now, both of these forces, the normal force and the force of gravity, the weight, they're all along the y-axis. So this problem, you don't even have to consider the x-axis because there are no forces acting along the x-axis. So what Newton's second law says is that the sum of the forces is equal to ma. And so that's what we want to do. And so in this case, we've got two forces. We've got the normal force, which is positive because it is pointing up. And then we have the weight, which is pointing down, and that's mg pointing down. And so that's pointing in the negative y direction. And so Fn is positive, mg is negative, and I can do now my sum of my forces right over here. I've got the sum of the forces. That's going to be equal to the normal force, which is positive, plus the weight, mg, which is negative, and all that's equal to ma. But what's the acceleration? In this case, the acceleration is going to be 0. How do I know that? Because the block is just sitting on the table. It's not even moving, much less accelerating. If it's leaping off the table, then you might say that there had to be some acceleration to consider. But it's not leaping off the table. It's not crashing through the table. It's just sitting there. Its motion is 0. Its acceleration is 0. Now, by the way, there's a little bit of a caveat I want to mention here. If something is moving with a constant velocity, its acceleration is still 0, and you just do the sum of the forces equals ma, and a is equal to 0, just like this. But in this case, it's not even moving, So we know the acceleration is 0. Fn minus mg equals to 0. And I can solve for the normal force, and when I do, I get the normal force is equal to mg, the weight. Now, let me mention something that's very important, because very often you're going to work problems in physics where the normal force works out to be the weight. And my students in the past have had a tendency to just kind of always assume that that's what it's going to end up being. And so they sit down to work a problem and they say, oh, there's a normal force that's equal to the weight. But this is a special case. This is not always going to be true. Not always true. Not always true. So, be advised, whenever you have a problem that has a normal force in it, you're probably going to have to calculate what that normal force is. So how do we calculate the normal force? Well, you do what we just did. You do the sum of the forces in the direction that the normal force is pointing in. You set it equal to ma, and then you solve for it. That's all you do. Just set up the Newton's second law equation and solve for it. We're going to do that a bunch, so I think you'll get pretty familiar with it pretty quick. Here's another example. So I've got my same block sitting on a table. I've got the weight, which is pointing downwards. I've got the normal force, which is pushing back. Now I've got an additional force, F, a pushing force that's pushing the block harder into the table. And we want to know, what is the normal force? Now, the way we do it again is we do the sum of the forces, and that's going to be, how many forces are in this picture? There are 3 forces. Which direction are they pointing? They're all pointing along the y-axis, either positive or negative, so there's no x to worry about. But what do I have? I've got my picture, I've got all my force vectors drawn as arrows on my picture, and then I've got my coordinate system to show me direction. I can see all my forces are along the y direction, so I just need to sum all the forces in that direction. And Fn is positive, mg is negative, F is going to be negative, and so I can just do the sum of the forces is positive Fn minus mg because it's pointing down, minus F because it's pointing down, equal to ma. But what's a? Again, my block is just sitting on the table. There's no acceleration. So the normal force is going to be mg plus F. How do I get that? I just do algebra. Move that over there, move that over there. They become positive. And so the normal force is mg plus the force of pushing. And I hope that that makes sense, because if the table is pushing back on this block, it's got to push back with the weight of the block, but then if someone comes and pushes down harder, it has to push back even harder to match that pushing force. So that's what this equation is telling us. The math is saying that the force that the table has to push back with is equal to the weight pushing the block into the table plus the pushing force pushing the block into the table. And so this is just, again, Newton's third law. The net force pushing it down has to be the reaction force of what gets pushed back with. What if instead of pushing down, you have a force that's pulling the block up? Now, we're going to assume that this force is not strong enough to pull the block off the table. If this force were big enough to pull the block off the table, what would happen to the normal force? It would just vanish, because the normal force is the force exerted on the block by the table, by the surface it's pressed against. So if I make this force bigger than the weight, it's just going to lift off the table, and you would have F and you would have mg, and you would say F minus mg equals ma, and you could calculate the acceleration. But in this case, it's not going to be lifting off the table, and so there is a normal force, and we know the acceleration is 0 because it's not lifting off the table. So we do the sum of the forces, Fn, which is in the positive direction, minus mg, because it's in the negative direction, plus F. Now this time F, which is pulling it up, that's in the positive direction as well. So when I solve for Fn, these guys get moved over to the other side of the equation, and I get the normal force is the weight, mg, minus the force of pulling. And imagine you have a bathroom scale sitting on the table, and the bathroom scale is reading the weight of this block. And so the second you start pulling it up, the reading on the scale is going to go down. That tracks with the normal force, because anytime you have a physics problem and it says, what's the reading on this bathroom scale that these blocks are resting on? You're just going to calculate the normal force because that's the force that the scale has to push back with. But the thing here is that this guy has a certain weight. It's pulling it down into the table. If you lift up, you're counteracting that weight somewhat. You're making it lighter on the table. So, if something is falling on your foot, some guy can come lift it off and they may not be able to get it completely off your foot, but they could maybe keep it from crushing your foot until someone else can come along and help them get it off. So just get the idea here that this normal force is something that you solve for. In each of these cases, how did I find the normal force? I said the sum of the forces equals ma, and I solve for it. That's all you got to do. Now let's do a tricky one. So I've got this block, which is in the corner of the room, and so it's up against the wall here, and it's on the floor there, and I'm pressing it downward at an angle of 30 degrees with a 100 Newton force, and it's a 10 kilogram block. And so what is the normal force going to be? In fact, you can actually see that in this problem, there are going to be two normal forces. There's the normal force of the floor, and then there's the normal force of the wall. Because this block is being pushed downward into the wall, downward into the floor rather, and pushed horizontally into the wall. How do I know it's being pushed horizontally? Because this force has a component that's in the horizontal direction, and it has a component that's in the vertical direction. So this force is going to be adding to the weight. This y component of the force is going to be adding to the weight, and this x component of the force is going to be pushing it into the wall. And so since it's being pushed into the wall is going to push back with the normal force of the wall. Since it's being pushed into the floor, you guessed it, the floor is going to be pushing back with the normal force of the floor. Okay, so let's set this up. We have our force, which is at a downward 30-degree angle. We have our weight. We have our normal force of the wall, and we have our normal force of the floor. Now this picture is a little bit confusing. There's so many different forces on it. One of the ways that you can simplify a picture like this is to draw what's called a free body diagram. And what the free body diagram is remember there's a rule. I can take each of these vectors and move them anywhere on the page that I want as long as I keep the same length and the same magnitude. So what I've done is I've moved all these forces over here and I've connected them all tail to tail so they have a common origin. And then I put my x and y axes at that origin to show me the directions. So this force, this is the normal force with the floor, is in the positive y direction. This other purple force is the normal force with the wall, that's in the negative x direction. The weight is in the minus y direction. The x component of the pushing force is in the x direction, the positive x direction, and the y component of the pushing force is in the minus y direction. And technically I could take this force and move it over here so that it's connected to that common origin. But this free body diagram, it's simply a way of seeing all the forces all at once in a way that's not all jumbled together and confusing. Now, there are physics professors who want you to draw a free body diagram for every physics problem you make. I am not one of them. To me, it's a tool. If this tool helps you understand how to draw the forces, then use it. If it doesn't help you, if it's just busy work, then for heaven's sakes, don't use it. So what you'll see in my lectures and in the videos that I'm making, that sometimes I draw a free body diagram, sometimes I don't. It just depends on the problem, whether or not it can help me. Now, how do I know that? Because I've got practice. So if you're working a problem and you're not sure whether it can help you or not, try it, draw it, see if it helped or not. You'll get a feel for it pretty quick if drawing these things helps you or not. But hopefully the idea of what to do when you draw one is pretty simple. Okay, so I've got my free body diagram here. I'm going to go ahead and just calculate all the forces that I can. So I know the weight is going to be m times g. The mass was given in the problem to be 10 kilograms. We know g is 9.81 meters per second squared. So the weight is 98.1 newtons. we know the force is 100 newtons at a downward 30-degree angle. And so the Fx is going to be 100 newtons times the cosine of the angle, and the Fy is going to be 100 newtons times the sine of the angle, so I can calculate those pretty quickly. Fy is 100 newtons times the sine of 30, that gives me 50 newtons. Fx is 100 newtons times the cosine of 30, that gives me 86.6 newtons. And I can note the directions here, so I could have easily called this minus 50 if I wanted to, or I can just note that it's downward, so I know that I've got the direction. This is 86.6 newtons to the right. I know that's going to be in the positive direction, so I can apply those into my summation. So let's do the sum of the forces in the x direction. There are only two. There's this Fx, which is F cosine of theta, and that was the 86.6 newtons. And then we have the normal force with the wall, which is in the negative x direction. All the other forces are in the y direction. And by the way, this force F that's at an angle, we've replaced it with these two blue forces that are along the x and y axes. So that force goes away once we break it into components. Remember, this component plus that component equals F. So we're just substituting these two guys for F, and that way everything is either pointing in the x direction or the y direction. So anyway, these are the two forces. I've got positive Fx. How do I know it's positive? It's pointing to the right, and that's the way I've defined my positive. Minus Fnw, that's because it's pointing to the left. And so, and of course they're equal to 0 because the acceleration is 0. And so I can move that guy over, and Fx equals Fnw, and we already calculated Fx to be 86.6 newtons. So that is both the force that is pushing it into the wall and the force that the wall is pushing back with. Now, if we want, we can go ahead and do the sum of the forces in the y direction, which is going to be Fn with the floor minus mg minus Fy equal to may, but of course we know that may is going to be 0. And so we can solve for Fn with the floor, the normal force of the floor, and that's going to be mg plus Fy, and we can plug in those values. That is 98.1 newtons plus 50 newtons, and so that gives us that the normal force with the floor is equal to 148.1 newtons. And so that gives us the two normal forces. We have the normal force with the wall is 86.6, and the normal force with the floor is 148.1. Okay, let's look at another example. This is example number 7. So we have two 10-kilogram masses that are connected by an ideal rope. An ideal rope is one where the mass is so small you can ignore it and it doesn't stretch. And what it means when we say that it doesn't stretch is that if this block moves over to the right 10 feet, this guy has to move over to the right 10 feet because they're connected. The rope is not stretching, so whatever distance this guy moves over, this guy's got to move over. They're moving together as one unit. Now, you can see this is a pretty complicated picture because there's two blocks and there's lots of forces. There's this 100 Newton force on block number 2. There's the weight of block number 2. And notice the subscript 2 with the M. We want to be very, very careful about our labels. The weight of block 2 is M sub 2G. And usually people would just say M2G, but M2G is the weight of block 2. And over here I've got a little 1 by the M to tell me that the weight of block 1 is M1G. And of course both of these weights are pointing down. Now, of course, the floor is going to be pushing back with the normal force, and block 1 is going to have its normal force, block 2 is going to have its normal force. And then there's the tension in the rope, and that's indicated by these two purple forces, F of 2 on 1 and F of 1 on 2. And so this is the force on block 1 from block 2. This is the force on block 2 from block 1. And these forces are all very carefully labeled. And so the problem here is boxed over here in green, and the question is asking us, given all of these forces, find the acceleration of the system and find the two forces on the two blocks, F12 and F21. Now the first thing that we can note is that on both of these blocks, you've got the weight, you've got the normal force, and this block is not at all going to accelerate in the y direction. It's not going to leap off the floor, it's not going to crash through the floor. The acceleration in the y direction is 0, so you can say immediately that these forces are going to balance. M1g is going to balance Fn1, M2g is going to balance Fn2. Now, if we look at the forces in the x direction, the horizontal direction, there's three. There's the 100 Newton force, there's F21, and there's F12. Now, one thing that is a little bit confusing to students when they first see this, and this is what we want to pay attention to, this force F is acting only on block 2. It's not acting on block 1. Only F21 is acting on block 1. And so when you do your sum of the forces, we can look at each block individually. We can isolate each block and calculate the appropriate sum of the forces. So over here we can see I've isolated block 1. Block 1 only has these vertical forces, which we're going to ignore because they don't matter, and then F21, which is making it move to the right. Oh, no. If we look at the other block, block number 2, we can isolate it and see that it has the two vertical forces, which we're going to ignore, but then it's got that 100 Newton force pulling it to the right, and the force of block 1 pulling it back, causing a resistance. And so if this were block 2 just by itself, this 100 Newton force would accelerate at a certain amount. But because it's tethered to this other mass, the amount of the acceleration is going to be reduced because this force is counteracting that force. Now, if we look at our block 1, we know that it only had F21 on it. So I can say that the sum of the force, if we look at just block 1, we can say the sum of the forces in the x direction is going to be just F21, and that's equal to M1A. Now we have to be very careful about the labels because this M is M1, not just any M. And so one of the things that makes physics challenging is how much you have to be very careful about paying attention to detail. And so you must have these things well labeled and you must be consistent with those labels. Otherwise, you are very likely going to get confused in when you start working the problems. Now, for the other block, we had the pulling force F, which was in the positive direction, and we had the other force F12, and so that was in the negative direction. And so we can do the sum of the forces in the x direction. Again, this is for block 2. The sum of the forces in the x direction are going to be F minus F12, and that's equal to M2A. And so we have two equations and two unknowns. Actually, we have three unknowns. We don't know F21, we don't know F12, and we don't know A. But because the rope isn't allowed to stretch, we can assume the A's are going to be the same. So we don't need an A1 and an A2 because our starting assumption was that the rope's not allowed to stretch. So they're going to move together as one unit and they're going to have the same acceleration. But we can simplify this because we know that F12 equals F21. How do we know that? We know that by Newton's third law. And we see up above here that F21 is M1A, so I can take M1A and plug it in right there. And so I can rewrite the sum of the forces in the x direction, and technically this is for block 2, and that's equal to F minus M1A, where we know that that was what F12 is equal to by Newton's third law. And so we've got F minus M1A equals M2A. And so I can just bring this guy over here, and I get F is equal to M1A plus M2A. So I had previously F is equal to M1A plus M2A. I can factor out an A, and that gives me F is equal to M1 plus M2A. and that gives me 100 newtons is equal to 10 kilograms plus 10 kilograms times the acceleration, and that gives me 20. I can divide 100 by 20 and solve for A, and I get the acceleration is 5 meters per second squared. And so that was one of the things I wanted to find. I wanted to find the acceleration. How do I do it? The sum of the forces equals ma. Okay, so I had previously this F, and I had F12 and F21, and I could have just simply, instead of isolating them and taking mass 1 and mass 2, I could have just simply started and said F minus F12 plus F21 equals M1 plus M2A. And that, of course, would be the total mass of the system. And so now I've got the sum of the forces equals ma. And so if we look at block 1, we know that in the horizontal direction there's only one force, F21, and F21 is equal to m1 times a. That's the acceleration of block 1 times the a, which we just calculated to be 5 meters per second squared. So if I plug it in, I can say that there's going to be a 50 Newton force to the right, and that's F21. Now, the other force, the force on the other block, which is in the opposite direction, that was F12, we know by Newton's third law that that just has to be equal and opposite. So that force would be 50 Newtons to the left. And on a test, you could say that. You could say by Newton's third law, it's 50 Newtons in the opposite direction, equal and opposite. But if you wanted to actually calculate it, you could just plug it in to the sum of the forces on block 2. So here are the forces in the horizontal direction on block 2. I've got F minus, so here's F, it's pointing in the positive direction, minus F12, it's pointing in the negative direction. These are the forces on block 2. We know they're equal to M2 times A. And so we can say F12, we just bring this guy over, rearrange everything with the signs, solve for F12, and we get, well, gosh, it works out to be 50 Newtons to the left, which we already knew, but it's comforting to see that the math works out.